Good morning, everyone. Okay, so for the last class of the semester, we're gonna do our content from our recitation. It's supposed to be this Friday. We're gonna move it and do it today. And I'll meet you on Friday for office hours. Okay, so let's look at, this is a Faraday's law application. So we have a long solenoid with radius r, and you have a current running through it with n turns per unit length. So this is your number density, right? Because it's infinite long, we really cannot say how many turns total. It will be many, many turns. But instead, we can say they are 100 turns per centimeter, something like that, right? N turns per unit length, that's your number density. So make a sketch of the magnitude of the B field as a function of distance from the center, goes for the inside and outside. You guys still remember what the B field is for a long solenoid?
E dot dl is equal to mu naught I enclosed.
Okay, and in this case is just current I, right? Current enclosed will be number density times the current. E dot into dl mu naught I enclosed. So remember, what kind of ampere loop did we choose?
We choose one which is where your B field is symmetric all along your Amperian loop. So in this case, it would be, I don't know, I'm not too sure.
So our B field is, we talked about the direction of B field, and we said it's in the Z direction for inside.
Right.
Right, and then you need to choose your loop to be in that same direction. So we need to choose a rectangle instead of a circle, right? And we also need, we also need to have current through. So which means your rectangle will be half in or half out. And thank you, Matthew, for your contribution. So it will be half in, half out. This is your loop. So BDL becomes B times L. And I enclose, you can see that this is I through the loop, this is I, this is I. There's many, many, many current through the loop, right, going through. So it would be N times I times, N times L times I. This is the total number of turns. So you can say, you can divide, you can get rid of L, right, because we're enclosing this length. So the total number of turns is number density times L. So B is mu naught and L, which is a constant. So to answer this question, to make a sketch as the radius R will be constant within 0 outside, right? Constant within 0 outside. Okay. Any questions about that?
I'm sorry, why did you multiply? Are you saying that your current enclosed is the number of turns times whatever length you have?
This is total number of turns. N times L is a number of turns.
Right, so NL would be times I would be your magnitude of I.
Will be in total I, because if I have one current through, I would say 1 amp. If I have 2 of them running through, I'll say 2 amps. If I have 3 of them, it's 3 amps. So each of them is I. I is, each of them is 1 amp, right? This is 1 amp, this is 1 amp. And
right.
There are 3 turns. So I need to count, okay, in the length, how many turns there is.
Got it. Okay, got it. Right, and that all, okay, I got it. Thank you.
Sure. Okay, let's look at the next question. So we derived this, right? We derived this one, but then now your current is changing, is decreasing with time. So as a result of that, your B field is decreasing with respect to time. Okay. And here we really just asking for a prediction. We can solve this, right? We can if you have a prediction, we can talk about it now. Where in space is the electric field 0? And where is it might be non-zero? Will it be inside the solenoid, outside, or everywhere? It turned out that we had talked about this in class. If we hadn't done this, one might be tempted to say the electric field will be 0 outside. Why? Because B is 0 outside. So I think maybe E is 0 outside. E would be non-zero inside, right? So that might be a reasonable guess. But we have already talked about, even if B is 0 outside, E is still non-zero outside and inside. So where in space is electric field 0? Where is it non-zero? Let's say it's non-zero both inside and outside. Because your B is changing. So it's like you're communicating with a point outside through a change in here. So that's the magnetic induction. So you can do your prediction what your E might look like, but we were just gonna go ahead with our calculation. Okay, so let's do the calculation. Faraday's law. So what is Faraday's law? Curve E negative dB over dt, right? So this is your differential format and this is your integral format, right? And the integral format is if you take the surface integral for both sides, ddt, dA, you integrate both sides and the left-hand side is equal to the line integral of E. And that is through Stokes theorem, right? Or curl theorem. So that this will equal to that. This is equivalent of saying this is your EMF, right? Your EMF is epsilon, which is E dot into dL, which is negative d phi flux over dt. So all of these different format, you should know that they all represent the same thing. This is your integral format of your Faraday's law. Okay, now let's try to do the calculation. We know that E, we have talked about this, E should be in the curl in the phi hat direction. So we want to draw a Faraday's loop, dL, we want to draw a loop that's a circle that's going around in the phi hat direction. So I wanted to talk a little bit about how the relationship of dL and dA, how do they relate to each other? So when we do this way, they already kind of showing you, okay, this is your, this is not a loop. This is your top view of the solenoid. This is showing the current. Okay, so this counterclockwise direction is showing the current flowing, right? Now, which gives you B is in the coming out of the page. So we can draw a little dot for B because that is your right-hand rule, right? B is coming out of the page. So the dA is an area bounded by this loop. So this is a loop and this is area. So an area could be pointing up or down depending on your loop. Which way are you bounded? Which way the loop is going. So I just want to show that it's not random where you choose to orient your loop. So for example, when you do B dot into dA, would it make sense to have B and dA to be in the same direction? So your dot product becomes a positive value, right? You can do it the other way around, but how about we choose our dA to be in the same direction as B so that dot product becomes 1. So which means you have an area, little area dA with your area vector pointing up. So what does that mean about the loop that is bounded? This loop must be counterclockwise, right? DL would be counterclockwise. If your DL is in this direction, which means that it gives you an open area pointing up. However, if you choose to look at your DL clockwise, that gives you an area pointing down. Does that make sense? The choice of DL is totally independent of your current. You can choose whichever DL you want to evaluate this integral. But we rather to choose a DL so that your DA and your B is in the same direction. So our calculation becomes more straightforward. Does that make sense? Any questions there? I know we often rush to calculations. So we never really paid attention to these little details. So sometimes you might end up with an extra plus or minus sign.
I'm just, when you say choose a loop such that, or choose a DA such that it's in the same direction as your DL, I'm not quite sure what you mean by that because they're perpendicular to one another, right?
They are. My point is your DL, this is a loop. A loop can bound a surface. So they are related in such a way that if your loop is going counterclockwise, we, by convention, this loop will bound a surface that's pointing upward. If your loop is going clockwise, then the bounded area is pointing down. Because if you only have a surface, there is no up or down. Who would to decide this is the surface, this is pointing up instead of pointing downward, right? So you need to give it a direction. So DL is sort of telling you that direction or what DA should be pointing at.
Right, and so you're telling us to be careful with the direction which we choose because we may drop a sign.
Yes, that's what I mean.
Okay.
Okay, so the thing is, if you have an EMF, right? If you can drive a current, the EMF. So E will be in such a direction. So given this choice of DL, if E is also driving in EMF that is counterclockwise, and DL, you choose to be counterclockwise. So E dot into DL will be larger than 0, and D dt, B dot into DA should also be larger than 0 because they're equal. So only if you're careful with your choice of your directions, then you can get the correct direction for your EMF. So if you ask, how do we know which way the EMF will be pointing at, is through your calculation of E. If you choose a DA and choose a DL that is consistent with your DA and then do the calculation, then you'll end up with the E that's either positive or negative. And that tells you if you connect a circuit, you will drive a current in this way or the other way around. So that tells you in which way your EMF will be pointing at. Of course, you can do the Lenz's law, but you can also figure it out from the calculation. Okay, now let's do the calculation. For inside, I'm going to draw a Faraday loop. DL pointing counterclockwise, so that gives me my DA pointing upward, which gives me E times 2 pi R. See, I don't know at this point the direction of E. I don't know if this EMF will be driving the current going this way or the other way around. I'm going to let my calculation tell me. Okay, so this is going to equal to negative d dt b dot into dA. dA is pi r squared because this is r, right? Pi r squared, and is really just dB dt, sorry. dB dt. Okay, let's look at dB dt. dB dt is negative c, right? B is b naught minus ct. So dB dt is negative c. I can plug that in. E 2 pi r negative c, negative c pi r squared. So this becomes positive, and you get E is equal to RC over 2. to get E as a positive number. Does that make sense? Is that what you're expecting? So
No,
what does this mean?
what was B is equal to minus? No, that doesn't make sense in my head. Shouldn't your B or shouldn't your E be in the opposite or opposite in sign of B?
Yes, Lenz's law, if it's opposing the change, right now B is decreasing. So to oppose.
Oh, okay, got it.
Yes, you wanted to produce an E that is in the same direction as B, and you did. So this positive sign say my EMF will try to drive a current that's in the same direction as your choice of DL. My DL is counterclockwise. This is showing that if you have a closed current, this EMF will try to induce a current that is also counterclockwise, that is try to produce a B out of the page. B induced should also be out of page. That is consistent with what we're trying to do, just fighting the change. So this is this meaning of why this has become positive. This becomes positive because of the choice of your, the loop direction and your area direction. Now use Faraday's law to calculate E outside. Okay, so I'm going to draw a Faraday loop outside. Again, counterclockwise. So E to pi r. You can see the area becomes pi r squared instead of pi a squared because you only have flux within this area. You don't have any flux outside. And dB dt, of course. Again, dB dt is negative C and positive C pi r squared. So E outside is going to be r squared C times r squared divided by 2r, goes in phi hat direction. Okay, so outside is also positive. Okay, the same as inside because B is decreasing. So you're trying to produce one that is in the same direction as your B. So to see this sketch of magnitude of E with respect to sort of distance, you can see it is linearly increasing R and 1 over R outside. So this is very, very similar to your B field for a thick wire, right? Because mathematically, the mathematical relationship is exactly the same. And that's how we use Faraday's law to calculate the E field produced.
Dr. Ryan, I know we've hammered in the point in the past, but I'm still trying to grasp my head around determining the direction for E.
Okay, sorry, say it again, your question?
I said I know we've been over this 1,000 times in the past, but I'm still trying to understand how we can determine the direction of our E.
Direction of your E field?
Yes.
Okay, so I want to combine your question with another question in the chat is, so if your answer is negative, you need to choose a different DL? No, you do not have to. If your answer was negative, simply say, so if my answer is positive, so how do I, okay, your question is, how do we figure out the direction of E? You can do, of course, you can do the Lenz's law, or you can look at here. Here it's saying, I chose my DL to be counterclockwise so that my dA is up, so that B dot into dA is a positive flux. So using that convention, I got a positive E, meaning my E is in the same direction as my DL, that is counterclockwise in phi hat. So E is also counterclockwise in a phi hat. So that's how you know the direction. If you had got a negative answer, simply mean that your E is clockwise in negative phi hat. You don't have to change your choice for your DL. Does that make sense? So if in this case, B is increasing, then dB dt is positive. If that's the case, if you go through this calculation, you will get a negative sign, right? And that's totally okay. That's simply saying you try to induce an EMF that is in clockwise direction, that if you have a closed circuit, it will try to induce also a current in the clockwise direction to produce a B in the opposite direction of the B that's given. Does that make sense? Did I answer your question? Both Sebastian and Nancy?
I I understand the sign convention. I'm just trying to figure out why it's in phi hat. Like I'm trying to figure out the relationship given some direction of B. How can we determine our direction of E?
Because E has only two possible directions, right? Either this way or this way, right? And if your E is this way, the other way around, you have already decided the dot product between E and DL. If E and DL are in the same direction, then it will reduce it to E times DL. So you will get, in this case, you will calculate the E magnitude. You don't need a negative sign. But if your E had been the other way around, you will see that negative sign coming out of your equation just to make sure these both sides match. Does that make sense?
Yeah, thank you.
Okay, another question Brendan asked, can we go back to the differential format to find whether the curl would be positive or negative? You certainly can. In this case, the curl of E is dB dt, and so dB dt would be, what is dB dt? Negative C. So it's less than 0, negative will be positive. So you can find the curl is positive, but I would argue that doesn't directly tell you the direction of E, right? You found something useful, you find the curl of E, but you don't know the direction of E. So you probably cannot get around by still to go through this process. Or if you don't like this, we did this in class. We said E is proportional to something negative, di, dt, d hat. So if everything is confusing, you can always go to this equation. This one is telling you if your current is increasing, then E will be in negative phi hat. So, okay, with the hypothesis that your current itself is in the phi hat, okay? Current is going counterclockwise. Then if current is increasing, E will be opposing that direction. If your current is decreasing, E will be in the same direction. Is that more straightforward?
So I know it wasn't my question, but can we say that that our E field is how do I describe that? Like I understand that the E field wants to oppose your change in B field, but is it always similar to the direction of your current? Like if we had some current moving in the positive Z direction and it was decreasing, would that mean that we would have some E field pointing in the negative Z direction or in the positive Z direction?
Yes, yes.
Okay, got it.
You can think of E field is what drives the EMF. The EMF is what drives the induced current.
Okay. Yeah, no, that makes
sense. You can just simply use the Lenz's law to think, well, if your original current is this way, then it is increasing, your E will be opposing it. So your E will be opposite. But if your original current is decreasing, then your E will be in the same direction as your current. So that'd be more straightforward.
Right. Okay. Thank you, Dr. Rand.
Okay, so that is the question. Now let's look at another one. This one has to do with motional EMF. We have a metal bar. This one is probably a very familiar setup from your intro physics, right? You have a resistor, you have this complete circuit, you have these two rails, you have metal bar sliding over. So this one gives you a complete a closed circuit. Because of the motion inside this B field, you're generating EMF and drive a current running through this loop. The first question, find the electromotive force. Well, it's really just the EMF, right? We find the potential. What is the potential in the circuit using Lorentz force law, showing the contribution of each piece of the circuit. And we know that really just one piece of the circuit, and that is generating EMF, right? We don't have to say you can say there's no motion from the other part, and the only contribution is from this leg. So let's do the first one. EMF is little f dot into dl. And here, the force per charge, Lorentz force law is saying F is Q V cross B, right? F over Q is just V cross B. It's going to be V cross B, dl. And you can see V and B are perpendicular, right? So it gives you V times B and the entire length, which is this L. This is L. So VB times L. Okay, and V cross B is the same direction as your DL. That's why the dot product becomes multiplication between these two. So your EMF is B times V times L. That's it, right? Okay. Second question. Now we can calculate EMF using the flux rule and not another rule. Does it agree with your answer? Well, it should agree. So let's do this way. EMF is negative B flux dt, which is d dt. Flux is B dot into dA. Okay, so now here is another opportunity. We can practice the idea of choosing the L and choosing our area. So this one is an EMF. EMF will be able to drive a current. So you can look at the EMF to be driving the current around a loop. Okay, so whichever you choose to evaluate this loop is totally up to you, right? But like we said, we tend to want to choose in dA that is in the same direction as my B so that this becomes positive. So we can do that again. Let's say your B is outside. So I'm going to choose an area that's also pointing outside. What kind of loop will give me that? I need a DL. I need a DL. Sorry, DL. That is counterclockwise, right? So dA is upward, which means my loop should have been DL should be counterclockwise. Okay, right? Which means if your EMF is also driving a current counterclockwise, you will get a positive value. If your current was going to drive a current the other way around, and you'll get a negative value. So d dt my B is oh, okay, my B is constant. So I'm going to take the outer side of the integral. The area dt, your A is in which direction? Your area is length times height. Height is L, and your length, you can call it dx dt, right? So this one, what does this one give you? It's give you the velocity of the bar. Does that make sense?
Absolutely.
Okay, so that's negative BLV. Okay, so now you got this equation and this two equations. Well, this one gives you a positive value, this one gives you a negative value, but that's okay. And how do you sort of resolve the issue that this one has a negative sign? This one has a negative sign simply because my convention. I've chosen a loop to be counterclockwise. The negative sign simply suggests my EMF will produce a current. I try to produce a induced current that is clockwise, is opposite of the loop that I choose. So induced current should have been clockwise. Induced current is this direction. The current will be flowing this way. This one we only calculated a magnitude. If we were to do the induced current, we can. So let's do V cross B. V cross B is downward. So produce a force driving your positive charges down, negative charges up. So that will produce a current flowing out of your positive terminal into your negative. That is clockwise current, which is consistent with this negative sign. So you say my two answer agree, right? Okay. Any questions so far? Before I do part C?
Excuse me.
Yes, go ahead.
So if I choose clockwise, DL is clockwise for part B. So what would be different for DA? Because we know that DA will flip the direction, right? But
Yes, if you choose,
calculation is how do we show it?
sure, if we choose DA to be downward, and DL is clockwise, then you know that B dot DA will be negative B times DA, because B is pointing out of the page and you choose your DA to be into the page. So you should have an extra negative sign. Your calculation would become negative D dt, D dot into DA, but you choose these two in opposite directions. So you would end up with an extra negative sign. So that become D dt, D times DA, D dA dt. That would just be positive BL.
I see.
Yeah. So that way I'll showing you your actual induced current is the same as your BL clockwise, right?
Got it. Thank you, Professor.
Sure. Very good question. Very good. Okay, now the third question is find the magnitude and the direction of the current through the resistor using the EMF. Okay, well, that's easy, right? We found the EMF. Current will be EMF over R, potential over resistance, which is BLV over R. And that's it. That's your current. And direction we already answered is clockwise. Part D, determine the motion of the bar after t equals 0. That is to find an expression for the velocity change with respect to time. The answer makes sense. Okay, so find the motion equation of motion for the bar, for D. So we can do, what we can do is to find the equation of motion, we can use Newton's second law, F equals ma. And let's see, what is the force, right? And we can plug in the force, and then we can, if we want a velocity with respect to time, we probably need a differential equation with v in it, so we can change a to dv dt. But first, let's try to find the force. So the force acting on the bar. We know that as soon as you induce a current, your current carrying wire will feel a force under the influence of your magnetic field. So that is a force. So this is a net force acting on the bar. So this is I dl cross B. Any wire that is carrying a current will feel a force under the B field, right? So that's the definition for that force. And we also, if you look at, 1 second, current. So you can, okay, so let's do the, we know how to calculate it, the magnitude, right? B is just B, current is just I. The integral of 0 to L over the length is just L. But we haven't added the direction. So let's look at the direction. The current is going which way? The current is flowing down. So dl is the same direction of your current. So L cross B is pointing to the left, right? So your current, so if this is your positive x hat, then your force would be in a negative x hat. That is the force. So the force is in a negative x hat. So I'm gonna do something just a little bit different because later on I want a velocity. So instead of saying negative x hat, I will say negative v hat because v is an x hat, which give you the same result. Okay, so this one is clearly showing you this force is opposing your velocity, is trying to slow you down, right? Which makes sense. Your force is always opposing the change in flux. So if you plug this one into your equation, you get negative BLI is equal to, oh, sorry, with a V hat is equal to M dV dt. Okay, and what is dV dt? dV dt is just V, dV dt is a V hat direction. I'm going to separate my direction from my magnitude. Since I have a V hat and V hat, I can get rid of it. You could have kept this as X hat though, and then you will write dV as in Vx hat. You will cancel your X hat anyway, so it will end up to be the same. Okay, so I get a differential equation for my velocity. I can plug in my current, which is BLV over R. I just calculated. My overall, I get dV over V is equal to negative V squared L squared over MR dt. Okay, so this one I can solve. This will give you a log, natural log. So I get V will be V naught to the e to the power of negative B L V squared L squared MR T. So this is your equations of motion for your velocity as a function of time. So the answer is, does this make sense? Let's see if it agree with our initial conditions. Initial conditions is at t equals 0, V is V naught. So if we plug in t equals 0, we get V equals V naught. So that makes sense, right? It is correct. And also, initial conditions we can do to other extreme at t approaching infinity. What do you predict about the motion of the bar? Should it continue moving, or would it have already slowed down at t equals infinity? V should be approaching what value?
V naught.
I'm sorry? 0, right?
Is V naught 0?
V naught is your initial velocity. So this is like, you give it a quick push, you give it initial velocity, but it quickly slows down.
Are we saying e to the minus e to the negative exponent goes to 0?
So yes, so this mathematically, as t equals 0, our expression tell me v equals 0, and physically that is what we expected. Physically also makes sense because you cannot be keeping that velocity because you have the magnetic force slowing you down, and
Right. Oh, that makes sense.
Lenz's law. So that all we checked the two conditions that all made sense. Okay, and he's seeing that it's actually slowing down exponentially, slowing down quickly. So that means if there is a problem saying the bar is maintaining a constant velocity of v naught, how could it possibly maintain a constant velocity? Meaning that there must be a external force is holding the bar and continue to move it with the same velocity, right? If I were to ask you to calculate what is the force by your hand or what is the external force, will you be able to calculate it so that it will move with a constant velocity? So for this problem, if I said the bar is moving with a constant velocity v naught. Question, what is the external force? Can you answer that question? You will say F external is equal to? If your bar is moving with a constant velocity.
Sorry, I thought that was rhetorical. Yeah, it's IBL. It's just what we found, except in
Yes, it will be equal to your magnetic force because only when your external force balance out the magnetic force, then it's possible to move with a constant velocity with 0 acceleration, right? So if it's constant velocity, you would know that what the required external force has to be. It has to be equal to whatever magnetic force of the bar is experiencing. But this one is really giving a initial velocity, but there's no other force acting on it. Therefore, it's going to slow down. Okay, one last piece. If you can test your answer using energy conservation, do that. If not, explain why not. So we wanted to, we kind of did sort of this in class, energy conservation, showing that we are generating energy in the circuit, right? We have heat, energy is dissipated by resistor, so that must be coming from somewhere. So we want to be able to show that. Let's do the last bit of derivation. So to verifying it using conservation of energy. So you can see that previously we have shown that the kinetic energy of the bar is decreasing, right? And that, so we have the kinetic energy is decreasing. We can show that the loss of your kinetic energy is going to you're generating your heat and power times time inside your circuit, right? Or you can view kinetic energy as work done by the force. Also relate that to the energy dissipated in the circuit. Those two are the same approach, right? So I'm just gonna do, since I have my V here, I'm gonna do the kinetic energy dissipation. So you can see you have a T here. Let me just, instead of doing kinetic energy goes to power, I'm going to the change of kinetic energy should equal to power. Okay, so my change in kinetic energy is d dt 1/2 mv squared. So it will be d dt 1/2 m. V is v naught squared e to the power of. So all of that, I'm going to copy it here to be 2b squared L squared T over mr. Okay, so all of these are constant. I can move it out of the equation. So d dt okay, so really just taking the derivative with respect to time. So I will get a bunch of constants coming out of this. which is negative 2BL squared over MR e to the same format. Okay, right? So let me see. I shouldn't have a positive. There isn't a not minus sign. Minus sign is here. So okay, so what do I get? I cancel 2, I cancel M, I get a negative B squared L squared V squared and over R squared. Shouldn't I get it over R squared? Oh, over R, I'm sorry. E to the entire stuff. Okay, so this is the change in kinetic energy over time. Or I can say this is the rate of kinetic energy decreasing, dissipation, the rate of change. Okay, and it's showing it's negative, right? Because kinetic energy is decreasing, so kinetic energy dt is negative. So now let's do dissipation in the power resistor, the power. So what is a power? Power is I squared times R. What is I? I is BLV over R times R. And V, what is V? So V is V squared L squared R squared V squared. Okay, V is V naught squared E to that entire thing, right? T over R. Okay, so what do I get? I get V squared L squared V naught squared over R E to the power of 2 V squared L squared T over MR. And does it equal to that? They are exactly the same, right? The rate of change of kinetic energy, because kinetic energy is decreasing, you get a negative sign, and the amount of that dissipated is exactly how much power is being consumed in your circuit. So you have demonstrated this part of energy is transferred or transformed from the format of kinetic energy or you can say it transferred out of the same system, it's becoming heat. So energy is not lost, right? It simply have changed the format in your circuit. So rate of kinetic energy dissipation is equal to the negative of power. So we have demonstrated energy conservation. This is the last bit. Any questions about this? Let me charge my computer. Otherwise, I'll be disconnected in a second. Any questions about this demonstration? Because I got another question in the chat. Any questions before I move on to answer the question in the chat? Okay, let's look at this question. The question is asking, can you explain the direction of current again? Wouldn't current be counterclockwise if B is pointing out of the page? Okay, B is pointing out of the page, but B is also increasing. So let's do the Lenz's law in this, okay? Let's try to use the Lenz's law to figure out the direction of current. Induced current, right? B, in this region, B is out of the page. And as your bar is moving to the right, the flux through this area is increasing. B is out of the page. Flux is increasing because you're including more and more area. As you move to the right, you're including more and more area. So that's why flux is increasing. Right? There are multiple ways to have induced current. You can change your B, you can change your area. So flux is increasing, you want to induce a current that is opposing the change. So to oppose the change, you wanted to, okay, it is increasing, I don't like it. I wanted to keep the way it is. So I want to induce a B field to be into the page. To generate that, you need a current that's clockwise. Okay. All right, so that's all for our recitation content. Any questions before we end today's class? Any questions?
Yeah, Dr. Ryan,
Yeah.
I was looking through the material and there's just a ton of stuff in between 4 and 7, or chapters 4 and 7. What should we prioritize for the test?
Between 4 and 7. Oh, okay. So you mean like all the content that will be covered on the final, right?
Yeah.
So, okay, there are 7 questions. You can kind of sort of do this sort of thing yourself. So there probably will be quite a lot of content on magnetostatics, chapter 5. We did chapter 4 and 6 relatively quickly. So whatever we did not discuss in class, I shouldn't expect you to do. So you should focus on the stuff that we did go over in class. But chapter 5, we went over the entire thing. So there probably will be quite a lot of content on magnetostatics, that including Ampere's law stuff. You should expect maybe 1 problem in chapter 4, electric field in matter. You should probably expect 1 problem in chapter 6, magnetic field in matter, but not too much because that's not what we focused on. And there should be some problem in chapter 7. Does that make sense? 1 or 2 problem in chapter 7.
Thank you.
Any other questions?
Just to check, how long do we get to do the final?
Final will be 195 minutes. That is 3 hours plus 15 minutes of uploading time.
Okay.
Any other questions, guys? Okay, if not, I have office hour later, after class, 12:45 to 1:45, or tomorrow from 11 to 12, and Friday from 12 to 1:50. That's our recitation time. So I want you to take advantage of that. Prepare and do your practice final. If you have questions, you can come and we will go over those questions. Okay. All right, so that will be all for today. I will see you guys perhaps at one of the office hours. Okay, good luck with your final. Bye.
Thank you, Dr. Ryan. We appreciate your help.
Thank you.
Thank you.
Bye-bye.
Thank you, Dr. Ryan.
No problem. Thank you. Bye-bye.